Okay, both batch and no plug, just batch and CSTR. Okay, you must know a design equation for that. So you can design a reactor. You must know flow through a tube, the Poiseuille flow, or in general flow / even basically flow through a pipe. Okay, so flow through a pipe in general, not just Poiseuille flow. And then also heat transfer, then as shell and tube, heat exchangers. Okay, and then also in addition to flow through a pipe, heat transfer in a pipe. Okay, so this is all you need to know. I mean, of course you need to know the stuff, but in terms of design equations, I'm going to just restrict myself to this for the quiz.
Can you repeat that second one?
Poiseuille flow or flow through a tube or through a pipe? So for example, if it's not laminar flow, if it's turbulent flow, I can give you a friction factor. And you must know how to calculate friction factor if you know how to calculate pressure drop if you know friction factor. What is friction factor for laminar flow in a tube? 16 over Reynolds number. So let's say in the problem statement I give you the friction factor for turbulent flow, we should be able to solve the problem for turbulent flow. Okay? Usually it's going to be some constant times Reynolds number to the power alpha. So instead of using Poiseuille flow equation, all you have to do is you have to figure out the flow rate or pressure drop versus flow rate relation for turbulent flow. So it's actually quite straightforward. You know, like I said, I give you the friction factor. So you just need to know the equation which relates pressure drop to flow rate for turbulent flow, if you know the friction factor. Okay. All right. Any other question? Yeah.
Are you going to post homework for this upcoming quiz?
Yeah, sure. Again, it will be the same thing. I'll post the homework. I will not collect solutions. I mean, I will not collect homeworks. Okay, can we move on? And from these, the type of optimization will be one variable or two variables.
What do you mean by shell and tube heat exchangers?
Exchanger. I mean, what else can I say about it?
What?
There's a shell, there's a tube. Liquid flows in shell, liquid flows in tube. Hot and cold, and Q is equal to delta UH, delta T LMTD.
Oh.
Shell and tube heat exchanger.
Oh.
Yeah?
All right.
Yes? Okay. Okay, and in addition, it could be one variable or two variable optimization, or it could also have uncertainty. Okay, so it could have uncertainty, so it could be one or two variable optimization with or without uncertainty. Okay. All right. So today I'm going to start talking about a somewhat different type of optimization. All the optimization problems that we did so far are what are called unconstrained optimization. Today I will do something that is called constrained optimization. Okay, so in optimization in general, let's say think of optimization of two variables. What you have is you have an objective function, right? Fx comma y, and you're trying to figure out the optimum values of this. means maximize or minimize. And so you have two unknowns, right? X star and Y star. Yeah, everybody's good? Today what we're going to do is we're going to try to solve, still we're trying to optimize f of x over y, but we are going to impose a constraint on it. We're going to say we're not interested in all possible solutions. We're only interested in a solution that satisfies the constraint g of x comma y equals to 0. So an example of this could be, again, let's think of a mountain. Okay, so you're skiing on a mountain, but now you're saying, I'm not interested in just the peak or trough of the mountains. I'm going to first cut a slice through the mountain, and that will give me a surface, and I want to look at the maxima and the minima along this surface. Does it make sense? Or it could be one of those ski tracks. So let's say you want to have a ski track along some certain contour, and then you want to look at the maxima and minima as you're coming down this track. Okay? So you don't look at the entire mountain, you look at only a certain region. Okay, does it make sense? All right, good. So first let's talk about this problem, a very simple problem, which basically comes from something, which will basically illustrate the concept. So let's talk about optimizing. Let's say you want to maximize area of a rectangle with fixed perimeter. Okay, so perimeter is fixed, and you want to maximize the area. So what it means is, let's say that you have a rectangle. So let's say the two sides are x and y. So what's the perimeter here? It's 2 of x plus y, which is fixed. Right? So that is fixed. So let's just call it P. And the area, which is x comma y, you want to maximize that. Okay? So first, let's just solve it. If you were to solve this problem, how would you solve it?
Solve for y or x.
Sorry, very good. The easiest way would be to from this equation substitute y in terms of x, plug it here. So this problem, as I'm posing it right now, is two unknown, one constraint, right? Two unknowns are x and y, one constraint is p. You can replace x in terms of y from this equation, plug it here. So then we have reduced that problem to what? One variable, unconstrained problem, right? Because you're taking the constraint out, you put it into the system, and so the new problem doesn't have a constraint anymore. All right, so let's solve that and see what we get. So from this equation, you get x, or let's say y, simply will be p over 2 minus x. Right? Sorry? What?
I thought the t was a z.
Oh, no. Better? I'm very, very bad at drawing. I used to get very bad grades when I was a student in drawing. That's because I'm a modern artist. Are my jokes that bad? Okay, even they are pretty bad, but they still break the monotony of the classroom, right? So you all laugh. So the importance, how good a joke should be from the context, right? I'm not a stand-up comedian. So my jokes, even though they're bad, they should actually qualify the good category. All right. So you plug this here. So you get area A to be y of x times. See, you all are laughing, so it's not. Okay. Well, that would be by definition, my jokes are really good. Okay, all right. So, therefore, you get this expression for area, right? So now the area as we have it is a function of how many unknowns? Just one, and so it's very straightforward. You take the derivative, set it equal to 0, and solve it, right? So now you can take the derivative, dA dx equals to 0. So you will get p over 2 minus x, right? Well, I mean, I'm going to do minus x and then minus x, right? So, well, so let's just, so this is the first term, and then minus x squared, so you can write, yeah, minus 2x if you want. I was going to write minus x minus x, but that's fine. And this equals to 0. So therefore, x equals to p over 4, and y equals to, from this equation, you can get p over 2 minus p over 4 equals to, obviously, p over 4. So you can see x equals to 1. And that means basically the optimum solution is the square. Now the interesting thing is, you kind of knew this right from the beginning based on symmetry. And that symmetry argument is always very powerful. Because right away you know in the beginning that x and y are completely interchangeable, right, in this problem. If x and y are completely interchangeable, then the optimum solution should also be such that x and y can be interchanged. Now, does it mean there is only one? That doesn't mean x has to be equal to y? No, not necessarily. But if there's only one solution, then that has to be the only solution. Or there could be two solutions. Let's say x and y are different, but then they are flipped, and there's another solution which is symmetric. But there's only one solution, which in this case you know there will be, because you know the equation will be quadratic. You take the derivative, there'll be only one solution. That solution must be x equals to y, right? Just based on the symmetry. Does it make sense? Symmetry arguments are always very useful. Then the problems get more and more complex. Of course, here the problem is very simple. All right, so this was easy. But in this case, the reason it was easy was because this